So tonight we're going to be going over this charge density problem, and we're going to be finding an electrical field component, specifically E of x, at the point 0, 0h on the z-axis, and this is our observer. So what you'll notice is, in all of these problems, you're going to be asked to find the electric field at some observer point, and the observer point is this point here that they give you. And it's good to label, or at least know whenever you're starting to learn this, that this is the observer. Another thing you have to notice is that this is the charge. So we're essentially putting a hoop at the z is equal to 0 axis that crosses x and y. So now you might ask, how do you start this type of problem? We're looking for the electric field component, so usually you want to start out with an equation that relates electric field to what you're given, or at least find a couple of equations that can end up relating them, eventually, of course. Now, one thing to notice is we are given the observer point in the z-axis, so before doing anything, you have to ask yourself, what coordinate system am I going to be in? In your crib sheet, please put the different coordinate sheet, literally put the entire note 6 into your crib sheet, or bring the entire slides, because if you don't know that, you're pretty much screwed for the entire exam. So please do that. Another thing is, we notice we're in the z-axis, or we are given a z-axis, so we know we're not in spherical. Now, it also tells us we have a phi here, so this gets rid of rectangular, so we are in cylindrical. Now, some past exams have tell you specifically which coordinate system you're going to be in, and that helps a lot. But if they don't, you have to make an educated assumption based on what they give you about which one might be the easiest. Now, in electric field problems, if they're asking for the voltage drop, you pick whichever one you want, but sometimes some are easier than others, and you'll get a little bit better at that as you do more practice. Nonetheless, let's finish this problem. We know we're in the cylindrical coordinates, so now what we should do is we should create an equation, or use an equation that relates electric field to surface charge density, or linear charge density. One equation is that E, hopefully y'all can see this, I'll use a better color maybe. E is equal to the contour integral, remember we're in linear, of the linear charge density from the, of course, where it begins from the charge, divided by 4 pi epsilon naught r squared, the unit vector r hat, dr prime. Now, what is prime? Prime we use as the initial point. This is given by Dr. Jackson in the book, I think, also. Prime signifies the initial point. That is this, the ring of charge, or wherever your charge is, your charge density is. That is what starts as prime. Now, the first step to this is to always define or identify what r hat is. This is going to be the r vector divided by the magnitude of that r vector. So now, again, what do you ask? Well, what is the r vector? Using the equation from note 6, we have the x hat, unit vector x hat, x minus the x prime. So I'm going to label this once and only once. This is our observer, and this is our where the surface charge density is. Okay, or not surface, wherever our charge density is. That's what that is. That's the position at which our charge density is. Now we do plus y prime, or y hat, y minus y prime, plus z hat, z minus z prime. And now we're going to fill this in. Well, where is the observer? What x value have they given us for the observer? Well, that's 0. So we're going to do x hat, 0 minus. Now, does the charge density have an x component? Does it vary with x? Yes, it does. It's a circle, and it's on the xy plane. So we're going to put x prime because x is going to change with time or wherever we are in time or space. Now we do plus y hat. Again, what is the y component of the observer? Well, that's 0 minus does the surface or does the charge density depend on y? The value y. Yes, it does. Y prime plus z hat. Now, does the observer have a z component? Yes, it does. It says it's h. Now, does our charge density vary with z? No, it doesn't. It's going to be lying on the xy plane or the z is equal to 0 plane. So this is 0. Now we can rewrite this. R is equal to negative x hat x prime minus y hat y prime plus z hat h. Now we have our r vector, but we need to find the magnitude of it. What do we do with this? Well, we take the square root of all of these squared, and I'm going to get rid of the negatives because when you square something, it's strictly positive. So x squared plus y squared plus h squared, right? Because the unit vectors go away, we're only talking about magnitude. And now there's something in here that we can simplify. We know because we're on the xy plane, if I were to draw this out again, we have this circle. And imagine this is a circle, right? And we have a radius a. Well, x is going to be what? That's not x, but this is x. X and y. This looks very familiar. We have a Pythagorean theorem or just a regular right angle triangle, right? So x squared plus y squared, the square root of this, is going to be equal to the hypotenuse squared, or a squared. So we can replace x squared plus y squared with a squared. Sorry, there should be no square root there. But x squared plus y squared is equal to a squared, so we can let this be a squared plus h squared. So if you were looking at these solutions and you didn't know where they got this a squared from, this is where they got it from. And they actually do something similar at the very end, which we'll go through. now that we have, we found our r hat, our unit vector, we can then find that we can put them together. Divided by the square root of a squared plus h squared. And by the way, they also let the magnitude of it be in this form, r by itself, not the absolute value symbol. It can just be written as r. And that's important because we also have an r in the equation, which we will then simplify or then substitute. So now, what do we do next? We found the r hat. What else don't we know in our equation? Well, there's one thing that, can be confusing. This r prime depends on what we're given. What does the charge density depend on? Does it depend on radius? Well, no, radius is constant. Does it depend on the z value? Well, no, z is going to be equal to 0, so that doesn't change, but it does depend on the angle, or phi prime, or phi prime. Okay, so that means we can rewrite this equation in terms of the contour integral, rho L phi prime divided by 4 pi epsilon naught. Remember, r is the square root of a squared plus h squared, and it's squared, so let's just write this as a squared plus h squared, times the r unit vector. Okay, so we drew this, we already wrote this, so I'm just going to copy and paste it. Okay, and then, well, it's not really going to be dr prime anymore. It's going to be d phi prime, because that is what we're changing with respect to. That is what the charge density will change with respect to. It won't change with r prime, and it won't change with z prime. So it's only going to be changing with phi prime. That's why we have that phi prime. Now we know rho L phi prime, the linear charge density, is going to be cosine of phi. Now do not forget this prime, because cosine of phi That's not technically right. We're talking about where we originate. Phi prime is for the charge density in uh, where like where we begin, right? We have this charge density here. I don't know. I mean, you could probably get away with not writing it, but just to make sure he doesn't take off any points for that, I don't think he would, but he might be picky, especially when you have different fees kind of running around. But in this case, you don't, so I wouldn't worry too much about it. Anyways, we're trying to find the sorry. Hopefully, y'all understand where I got this from. Hopefully, it's been clear. The next part is, what are the bounds for our integration? Well, looking at our picture here in the xy plane, what would be the bounds of integration of a circle? For phi, remember, phi is going to be this angle. Phi prime, sorry. Well, that has to be 0 to 2 pi, right? So we're going to erase this c and go from 0 to 2 pi. This might make it a little easier to figure out. Now, what else do we have? Well, we want to find the x component. So that means this y hat and this z hat will go away. We do not need them. We only need this x hat component. And whenever you do the x component of something, you do not have to carry that x hat. Drop it and leave only the magnitude of that component. So now what do we have? Well, we have the integral from 0 to 2 pi of cosine phi prime x prime divided by 4 pi epsilon naught. Well, a squared plus h squared is, also this one here, so let's write this. A squared plus h squared times, and I'm going to write this in exponent form. When you multiply something that has the same base, you have to add the exponents. So what does this equal? This equals a squared plus h squared times 1 plus 1/2, or a squared plus h squared to the power of 3 over 2. So that's how they get the 3 over 2. This comes up very, very often because the basis of our electric field equation has an r squared, and you have to multiply it by an r given the unit vector. Anyways, now what do we have after this? Well, we have the x prime. Now we have d phi prime. Hopefully we got everything here. Now we have to figure out what is x prime, because it's not so apparent what that might be. Also, I forgot the negative. You can't forget this negative. I'm going to put it on the outside. It might not be apparent, what exactly this value is. What might it be? Also, I think I'm missing an A somewhere. But I'm not seeing... I'll be right back. Yeah, sorry, I totally forgot. This is why it's important to have that Note 6 coordinate system out. Because in the cylindrical coordinate system, what is dr? Let me make sure I write this exactly where it needs to be. dr prime in our case is going to be equal to, in the cylindrical coordinate system, rho prime d, or rho hat d rho prime plus phi hat, which is what we're trying to do, rho, I guess, hat or prime d phi prime plus z hat dz prime. Now, you have to remember rho is going to be the radius, which in our case is a. Okay? So we're going to leave that's where the a comes from, because this d phi prime comes with its own little a. So we have an a right here. We're going to multiply it to everything. Now we can move on. I'm sorry, I knew something was wrong. I forgot. You can't just say, oh, it changes with time. You have to literally use unit or note 6 in differentials to plug that into your cylindrical coordinate system. Be very, very careful, because whenever you have to plug in dr for, I believe, Gauss's law or something like this, you have to use this, and sometimes it's very hard to memorize. Maybe eventually I'll get there, but right now you just have to use the notes. I mean, I literally would have messed this up. I would have missed an A, and then the equation just would have been wrong. So now, anyways, x prime. X prime is equal to what? Well, x prime, remember what we did? We drew a circle. What is this x component? Because that's what it is. X prime is the component of our triangle. Well, if this is phi prime, x prime is equal to the adjacent, right? So we have a cosine of phi prime. If you want to see the steps to this, you can see cosine of phi prime is equal to the adjacent divided by the hypotenuse, which then gives you x prime is equal to a cosine phi prime. So hopefully this made sense. Now what you do is you plug that in, a cosine phi prime, plug that into here, into this equation, a cosine phi prime. And now what do we know? Well, we get negative, and I'm going to move everything that does not have phi prime to the front, outside of the integration. So what is that? Well, that's a squared divided by 4 pi epsilon naught a squared plus h squared to the 3 halves. Integration from 0 to 2 pi of, what is that, a times a, not a times a, cosine phi prime times cosine phi prime, which is cosine squared phi prime, d phi prime. Now for this, you can use a half angle identity, I believe, or a double angle identity. I believe it's a double angle identity. But I'm going to use just something from the integration table. What this ends up being is this ends up being negative a squared. You can also plug this into your calculator if you wanted to do it. I definitely recommend you do this on your calculator. You don't want to mess up simple integration. What we end up getting, I say simple integration, and then I'm literally like, putting it into something on Google or something, whatever. Anyways, that ends up being pi. Well, what do we know? We have a pi in the numerator and denominator, so we can then cancel them out. So they go away, and that's our answer. Move this over. That is the x component. Don't forget your units, volts per meter, because it varies with distance. All right, so that is our answer. Hopefully this process made sense and it was very easy to follow. If it's not very easy to follow, please reach out to me. I'll make more videos on this, especially because this is most certainly finding the electric field given a charge density is most certainly going to be on the exam. You have to be very comfortable with using linear, surface, and volumetric charge densities to find, the E component. One, of course, recommendation, I've said it a couple times already in the video, is please make sure you have the entirety of Note 6 or have all of the coordinate systems known for the exam. If you don't know them for the exam, you're kind of screwed. Everything deals with it. Anyways, hopefully this made sense. If you have any questions, please reach out to me. If not, good luck. And I hope y'all watch more videos. Thank you.